Hi folks, welcome back to Physics with Captain Rod. Making this video here to demonstrate how to calculate the frequency of a mechanical vibrating system. So what we're looking at for our example here, we're looking at what's called a simple pendulum, which is basically a mass on the end of some sort of rope or string. And we're going to imagine this object kind of displaced from equilibrium, some angle theta here, and released. Now, variables of the problem that are kind of important. All right, so the length here is going to be important, and then this guy here has a mass m. Now, to write the equations of motion for a vibrating system, there's two ways. Method number one is to draw a free body and apply Newton's second law. You just need to write it in such a way that the equation's good for on either side here as this thing rotates back and forth. Or you can write an expression out for the total mechanical energy of the system and differentiate it. As long as there's not an external force or some sort of damping to change the energy of the system, then the time derivative of the total energy of the system is 0. So this mass here, we're going to imagine this being kind of a generic theta. This thing's rocking, or is oscillating back and forth. At any given time, the total energy of the system is the sum of its kinetic energy, which for now I'm just going to write 1/2 mv squared, plus its potential energy, which in terms of the variables listed, let's see, can be expressed, how about minus mgl cosine theta. The mgl cosine theta is this height, and what I've done is I've written the potential energy term with respect to a datum here. Now, the v and the theta are related. I'm going to use theta here to track where this thing is at. So the v can be related to theta from the definition of a radian. Remember, as this thing moves along this path here, it's traveling what's called an arc length. Oh, pardon me. And from the definition of radian, the arc length is equal to r times theta. When we differentiate this is going to be s dot. That's the speed here that I'm calling v, is equal to r times theta dot, if r is fixed. So this kinetic energy term, we can write 1/2 m r times theta dot squared, and then minus mgl cosine theta. Okay, so I think we're ready to roll here. So now, next step, taking note that there are no non-conservative forces acting on this animal. The only forces acting on this mass as it oscillates back and forth is the gravitational force down, which I've taken into account with a potential energy term, and a tension that kind of acts up and right. That tension doesn't affect the energy because the tension always makes a right angle to the velocity. So there's no work term for that tension. So if we take the time derivative now of this entire equation here, the time derivative of the left-hand side of this is 0. Okay, let's take a look at what we got going on here now. 1/2 m r squared. These are all constant. The time derivative of the theta dot squared, let's see, we bring down the 2, that's actually going to cancel that 1/2, so we're going to have mr squared theta dot to the first power, and again this is theta dot squared, so when you time differentiate it, you'll end up with a theta dot to the first power, but you have to chain rule it. Theta dot itself is time dependent, so when we hit it with a time derivative, we get a theta double dot. All right, looking over to this term here, so we've got minus mgl, all constant. Theta, however, is changing, so this term needs to be time differentiated. When we differentiate cosine, we get minus sine. That's going to do this. Then we have sine theta times, and it has to be chain ruled, theta dot. Right. So this is what we get if we time differentiate this middle equation here. Now, some observations here. This theta dot is on every term, or we can divide both sides by theta dot. Here's our second derivative here. So in differential equation theory, it's very common to write highest derivative first with a 1 in front of it. So what I'd have to do is divide by mr squared. So this is now going to read theta double dot plus, let's see, dividing by mr squared. These are going to go away. GL over R. Okay, so the R and the L are the same here. The where did that come from? Yeah, this right here, this R was for the radius of curvature, which is essentially the length of the rope. You know, it might be the length of the rope plus a little tiny bit more, but you know, if the rope is tied on right here, we'll just say that the rope is tied right to G here, right to the center mass of the system. So the R and the L are the same value in this. So when we divide out that L squared, let's see, we're going to have GL, we're going to divide one out. We're going to have here, dividing by L squared. So this term's going to be G over L sine theta is what that's going to be. And then equals 0. All right, so here's the equation of motion right here that describes this pendulum. Now, with the sine part here, this is a highly chaotic system. All right, this becomes a nonlinear differential equation, very difficult to solve. So what I'm going to do here is I'm going to use what's called small angle approximation. As long as theta is small, then sine theta is approximately equal to theta. If you think back to calculus, one of the famous limits you should have studied was the limit as theta goes to 0 of sine theta over theta, and that goes to 1 as theta goes to 0. So what I'm going to do here is approximate this to theta, and this is now going to read theta double dot plus G over L times theta equals 0. Okay, now what we have is something that's very easily solved. I'm going to take a moment and get rid of stuff that I don't need anymore. All right, take this guy up here. Now, second derivative plus a constant times theta equals 0. So this equation has trig solutions. So the solution of this equation, it can be expressed something like this. Theta equals A sine, I'm going to go ahead and write it, omega t plus B cosine omega t. Again, where the omega is what's called the angular frequency. This is the general solution of a differential equation in this form. Now, depending on whether or not you have initial conditions, that would dictate kind of how we proceed here. If we had initial conditions, like something like at theta equals, or at t equals 0, maybe theta equals 5 degrees or something, I would typically apply those conditions first. Here we don't really have initial conditions, and they're not important. The frequency of vibration of the system does not depend on time. It's very easy to show that. Set up some sort of physical pendulum here, put it in simple pendulum. Physical pendulum is something else. Put it into motion, basically pull her back, let it go back and forth, and pretty well no matter when you start timing it, you'll find that the frequency is not changing. So it's not time dependent. If it's not time dependent, that means that basically I can choose either of these terms. So what I'm going to do is I'm going to just throw this guy away. Now, as far as the frequency is concerned, what we want is this. This is the angular frequency of the system. It's related to the linear frequency by, let's see, the angular frequency is 2 pi times the vibrational frequency of the system. We can get this by solving the differential equation. The idea is we have to sub this term in and look for the omega. Now, to do that, we're going to need the theta double dot. So theta dot is equal to, time differentiating this once, a omega cosine omega t. And then theta double dot, differentiating again, the derivative of a cosine function being a sine function, minus a omega squared sine omega t. All right, so now we're ready to roll. We're going to sub this here. And then we're going to sub this here. Equals 0. Make myself a little more room here. All right. Factoring. Next step here is to do a little bit of factoring here. You notice we can factor out a sine omega t. Oops. G over L times theta. Ooh, theta was a sine omega t. I forgot an a there, folks. I was looking at this going, this doesn't look quite right. My apologies for that. Got that a right there, but when we sub this value right here, it's G over L a sine omega t. So we should have an a right there. Sorry about that. Which means the a also can be factored out because it's common to both terms. And then we're left with, let's see, minus omega squared plus G over L equals 0. All right, so what we have here now is we have an equation where we have the product of three things, 1, 2, 3 equals 0. Well, we can't really allow this one to be 0 because if it did, we wouldn't have a solution left, right? Remember, we're saying that we believe our solution looks like this. Same thing with a. If a were equal to 0, this would equal 0 and we wouldn't have a solution. Those are called trivial solutions. They do in fact, solve the differential equation, but they don't describe this system. Right? So this is the only physical possibility here that allows us to describe this system. It's pretty easy to solve for the angular frequency, square root G over L. Now, the angular frequency is 2 pi times the vibrational frequency of the system. So the vibrational frequency of the system, 1 over 2 pi root G over L. You'll notice that really the only variable here is length. You can modify this system according to the length of the pendulum. Notice that as the length gets larger, the frequency would go down. You can also calculate the period very easily. The period is 1 over the frequency. Let's see, and I guess that would be 2 pi root L over G. Okay, so again, the idea here was how to calculate the frequency or period of a mechanically vibrating system. Start by writing out an equation that represents the total energy of the system. Hit it with a time derivative and simplify, and you'll get some sort of equation here, a second order differential equation that describes the system. If you have sines and cosines, if they show up in the system, small angle approximations look like this. Sine thetas approximate to theta. Cosine thetas approximate to 1 for small thetas. Then you write out what's called the harmonic solution, which looks like this. Now, if you have initial conditions, typically apply them. You could end up keeping the sine term or the cosine term, or sometimes a combination of the two. If you don't have initial conditions, you are free to choose the initial conditions. If all you want is the frequency is not time dependent, you can choose the initial conditions. Basically, pick one of these terms, either this one or this one, throw the other one out, sub it, and that's what you're looking for right there, the omegas. Those will give you the angular frequencies of the system. So, hope this video helps demonstrate how to find the frequency of a vibrating system. Have a great day.